Okay, so titrations and pH curves is a subject you would have covered in General Chemistry 1. At least you would have covered the idea of titrations. And so a titration is just a technique that we use to determine the concentration of an acid or base in solution. And so we start with a standard solution, or what we call our titrant, which is a strong acid or base solution that we know the concentration of. So in here, sometimes we call it the stock solution, but a titrant, again, we know the concentration of what's in the burette, but the analyte is the solution that has an unknown concentration. So our analyte is in here, and then what we're going to do is we're going to put an indicator in the Erlenmeyer flask containing the analyte, and when we have a color change, we know that our titration has reached its endpoint. So again, these are concepts that you would have seen in General Chemistry 1, but what we're going to do in this class, General Chemistry 2, is we're going to actually follow a titration all the way through the titration, and we're going to look at the pH at different points along our titration. And so we're going to start here, a strong acid being titrated with a strong base. So it says, consider 0.1 molar solution of hydrochloric acid. You take 40 milliliters of that solution and you're going to titrate it with 0.2 molar sodium hydroxide. So the sodium hydroxide has a concentration that's twice as high as the concentration of the hydrochloric acid. Calculate the pH after the following volumes of sodium hydroxide have been added to the acidic solution, and we're going to identify the equivalence point. And the equivalence point, I know we're not there yet, but the equivalence point is going to be the point where the number of moles of acid are going to be equal to the number of moles of base. All right, so the number of moles of acid are going to be equal to the number of moles of base. Well, let's start out with the first one. So we're going to start here with 0 moles of sodium hydroxide. So that means that all we have is our 0.1 molar solution of HCl. So this is pretty quick because we know HCl is a strong acid. It's going to dissociate 100%. Maybe I'll put the whole equilibrium here. So it's going to dissociate 100% in water because, again, it's a strong acid to give us hydronium plus chloride. Well, we know that chloride won't affect the pH in any way. And so we're going to make our ice table. So we have 0.10 molar here, 0 and 0. Of course, since it dissociates 100%, we're going to lose all of our HCl. And our stoichiometry is 1 to 1 to 1 for HCl, hydronium, and chloride ion respectively. So we end up with 0, 0.10 molar, and 0.10 molar. And as I stated before, the concentration of the chloride, well, the chloride doesn't affect pH in any way, but we know that the concentration of our hydronium ion does affect the pH. And so we're going to calculate our pH is going to be equal to the negative log of the concentration of hydronium. So our pH is equal to the negative log of 0.10, and we get that our pH is going to be equal to 1.00. Remember, we have 2 sig figs in our concentration, and therefore we report 2 decimal places in our pH. Okay, so now we're going to move on to our 18 milliliters of sodium hydroxide. So we again have 40 mils of our 0.1 molar HCl, and we've added 18 mils of our 0.2 molar sodium hydroxide. So we're reacting HCl with sodium hydroxide, so HCl plus NaOH. And of course, that's going to give us sodium chloride plus water. So let's make another ice table. And let's figure out what our limiting reactant is here, and let's figure out what our concentrations of all these species are at, or once the neutralization is complete. Then we can make a new ice table with whatever is left over. All right, so we have the initial number of moles of our HCl. So we know that it's 0.0400 liters, and we're going to multiply that by the concentration, which is 0.10 moles per liter, like that. So we end up with 0.0040 moles. Running out of space here, so I'm just going to move all this over. So I'll put all this over here. There we go. Now for our sodium hydroxide, we have 18 milliliters. So we have our 0.01800 liters multiplied by the concentration, 0.20 moles per liter. And that means the initial amount of sodium hydroxide is going to be 0.0036 moles. Okay, now this is what we're starting out with. So you can see here that the sodium hydroxide is the limiting reactant because we have 0.0036 moles and we have 0.0040 moles of HCl. So let's figure out what our change is going to be. So we're going to lose all of our sodium hydroxide, 0.0036 moles, and we're going to lose 0.0036 moles of our HCl. Of course, we're going to gain 0.0036 moles of our NaCl, but we know that sodium doesn't affect the pH of a solution and chloride doesn't affect the pH of a solution. So we can kind of ignore that. But at equilibrium, we've gotten rid of all the sodium hydroxide. It was the limiting reactant, and we're left over with 0.00040 moles of our, it actually should be 0.004 moles of our HCl. So now what we need to do in order to determine the pH of the solution, the only thing that we have to worry about is our HCl. And so we're going to need to calculate the concentration of our HCl because our HCl, we have our HCl, remember the HCl is the only thing left over. Our HCl is going to dissociate 100% in water to give us hydronium and chloride ions. Well, we have 0.0004 moles, but what's our total volume? Well, we have 40 plus 18, right? We added 40 mils of our HCl and 18 mils of our sodium hydroxide. So that makes 58 milliliters. So if we divide that by 1,000, we end up with 0.05800 liters. And that means the concentration of our HCl is 0.0067 molar. And instead of me making an entire ice table for this one, you guys should know by now that since my HCl dissociates 100%, that at the end of my ice table, the concentration of my hydronium is going to be what? It's going to be identical to the initial concentration of my HCl, which is 0.0067 molar, like that. So the pH of the solution is going to be the negative log of 0.0067 molar. And so let me clean that up. And so when you punch that in your calculator, you end up with your pH is equal to 2.16. Does this make sense? Sure it does, because we started out with 0 mils of our sodium hydroxide and our pH was 1 at that point. Now we've added 18 milliliters of sodium hydroxide, and so the pH has increased, right? We still only have HCl, but its concentration is not as high, right? In the first problem, the concentration of our HCl was 0.1 molar, and now it's gone down to 0.0067 molar. So of course the pH is going to increase. Now, in the next part, we're going to add 20 mils of our sodium hydroxide. So I'm going to move to a clean slate for that. All right, so now we've got 20 mils of sodium hydroxide at a concentration of 0.2 molar. So if you're a student in math, and I know you all are, you can see that if the concentration of the sodium hydroxide is double that of the HCl, we're adding half the volume of sodium hydroxide. So this should be the equivalence point, and we're going to see that it is. So we know from the previous slide that we're starting out with 0.0040 moles of HCl. But if we look at the number of moles of our sodium hydroxide, we have 0.02000 liters multiplied by our concentration, 0.2 moles per liter. We multiply that out, and what do we get? Hey, what do you know? 0.0040 moles. So you can see that the number of moles of HCl and the number of moles of sodium hydroxide are exactly equal. So let me just move this over a bit here. Okay, there we go, because this is our ice table. I'll fix this up too. All right, so we have an equal amount of both of these, and so when we do our change, we're going to lose everything here. We're going to lose everything here. and we're going to gain 0.0040 moles of NaCl. So at equilibrium, we have nothing here, and we have 0.0040 moles of NaCl. Now we could go ahead and we could calculate the concentration of the NaCl, which would be the 0.0040 moles divided by the total volume, which would be 60 milliliters. But we know that sodium chloride, what, does not affect, it doesn't affect pH. And so we are at the equivalence point. So we can write that down here. We are at equivalence point, okay, since the number of moles of acid is equal to the number of moles of base. And so since all the titrant has been completely neutralized by the analyte, again, we're at the equivalence point. And so since all the HCl is gone, all the sodium hydroxide is gone, sodium chloride doesn't affect pH. So we can just write down our pH is going to be equal to 7.00, right? This is going to be neutral. Okay, there's no species in here that are acidic or basic. Now, what do you think is going to happen in part 4? Well, I think that the pH is going to skyrocket because now we know that since we're adding more than 20 mils of sodium hydroxide, that all of the HCl will be neutralized and will be left over with just sodium hydroxide. So let's see what happens. All right, so here we go. We know from before that we have our 0.0040 moles of HCl, right? So we're starting it with every time, right? 0.1 molar solution, 40 mils of it. We've done the math a couple slides ago. So now for our sodium hydroxide, we have 25 mils, so 0.02500 liters multiplied by 0.2 moles per liter, and we end up with 0.0050 moles. So you can see that now we have more sodium hydroxide, right? We have more sodium hydroxide than we do HCl. So let's do our C. We can see the HCl is the limiting reactant here, so we're going to lose all of that, the 0.0040 moles. We're going to lose 0.0040 moles. We can write in here, we're going to gain 0.0040 moles, but again, the NaCl doesn't affect pH. So at equilibrium, we have no HCl. We have 0.0010 moles of our sodium hydroxide, and we have 0.0040 moles of the NaCl. But again, that doesn't affect pH whatsoever. And so now we have to figure out what the concentration of our sodium hydroxide is, right? Because it's all we have left over. So we can say we know that sodium hydroxide is going to dissociate 100% to give us sodium plus hydroxide. We know that because sodium hydroxide is a strong base, right? So what's the initial concentration of our sodium hydroxide? It's going to be 0.0010 moles, right? What I have highlighted in yellow divided by the total volume. Well, what's my total volume? I have 40 mils plus 25 mils. That gives me 65 milliliters. So I have 0.0650 liters, and that equals 0.015 molar. Now, there's no need to make a huge ice table here, really. You can if you want to, but we know that sodium hydroxide is a strong base. It dissociates 100%. The stoichiometric ratio of sodium hydroxide to hydroxide is 1 to 1. Therefore, the concentration of my hydroxide ions are 0.015 molar. So instead of evaluating the pH, what I'm going to do is I'm going to evaluate the pOH, and I'll say pOH is equal to the negative log of the concentration of hydroxide ions. So pOH is going to be equal to the negative log of 0.015 like this. So we get that pOH is equal to 1.82, but that's not the pH. The pH is going to be 14 minus 1.82. Remember that pH plus pOH is equal to 14. So that's how we solve for pH, and we end up with 12.18. Well, was I right? Yes. We can see that the pH skyrocketed when we added an excess of sodium hydroxide, when we passed that equivalence point where the number of moles of acid was equal to the number of moles of base. Now let's see what this looks like on a graph. All right, so here's the titration curve of what we just did, the titration of a strong base and strong acid. So we're starting out with a strong acid and we're titrating it with a strong base. And so you see here the pH is on the y-axis. Well, the pH is the pH of the solution in the Erlenmeyer flask. And then you see there's the volume of the sodium hydroxide added. Well, that's the sodium hydroxide that came from the burette. And what do you notice? You notice at the beginning of the titration curve that at the very beginning, so we're starting right here, okay? At this point, we have a pH that's equal to 1 at the very beginning. And at first, before you added the base in excess, at first the concentration of the hydronium was in excess, and so the pH stayed very low. But then as soon as you reach the equivalence point, you can see that it just skyrocketed. Where's my highlighter? It skyrocketed very quickly, and to the point where we get an excess of hydroxide ions, and then the pH is going to be very high, as you see here. So our equivalence point for a strong acid and a strong base is going to be when the pH is neutral. So some of the features of the sample of the titration curve of a strong acid and strong base is that it's symmetrical around the equivalence point. The equivalence point is going to be at a pH of 7, and the pH rises steadily, then very sharply, then it goes steadily again. So good indicators, it says, are going to be ones that are whose pH are in the vertical line of the curve. So if you are looking for an indicator, and we're going to talk more about indicators later on, you're going to look for an indicator that's going to have the pH in the range, you know, somewhere in here in the vertical part of the curve. So you can see it's actually a pretty big range here of indicators that you could use for the titration of a strong acid with a strong base.